Hello my dear friends, we are Safe Gels, ready to help you. Now let's begin without any delay. Play intro, please. Compartment models. Pharmacokinetics. Definitions and introduction. Pharmacokinetics, defined as kinetic of drug absorption, distribution, metabolism and excretion, and their relation with pharmacologic, toxicological and therapeutic response. Two aspects of studies are theoretical, development of pharmacokinetic models to predict drug-drug disposition after administration, and experimental, development of biological sampling techniques, analytical methods to measure drug concentration in biological sample. Dosage regimen, frequency of administration in a particular dose. Pharmacokinetic analysis. Model-based analysis. Compartment model. Mammillary model. Catenary model. Physiological model. Perfusion limited. Diffusion limited. Distributed parameter model. Model-independent approach. Non-compartment analysis. Now discussing about compartment models. These interpolate the experimental data and allows to estimate the drug concentration with time. These are hypothetical model. Certain assumptions are: body is represented as series of compartments either in series or parallel, and considered as tissues have similar drug distribution. In each compartment the drug is considered as rapidly and uniformly distributed. Entry and exit of drugs are described by first-order kinetics. Type 1 of compartment model is mammillary model. It's described by two parameters, namely volume of compartment and elimination rate constant. This pic is showing main types of mammillary models being used in kinetics. Second type is catenary model. It's a realistic model. The pic is showing basic concept of this model approach. Physiological model. Drawn on basis of known anatomic and physiological data presenting more realistic picture of drug disposition in tissues and organs. It's of two types. Number 1 is perfusion rate limited, also known as blood flow rate limited, based on drug movement within body region is much more rapid than its rate of delivery to that region of perfusing blood. And second type is diffusion limited model, also called membrane permeation rate limited, applicable to highly polar, ionized and charged drug. Cell membrane act as barrier for drug that gradually permeates by diffusion. The image is showing basic concept of physiological model approach in kinetics analysis. Non-compartment analysis. Based on drugs or metabolites follow linear kinetics, and this can be applied on any compartment model. It's based on statistical moments theory, involves collection of experimental data following single dose of drug. Now here we see graph between concentration and time. AUC and AUMC is being shown, and T1/2 with concentration is shown with respect to AUC and AUMC. Some kinetic parameters being discussed are: AUC is area under curve, the total integrated area under plasma level time profile, and express the total amount of the drug that comes into system circulation after its administration. Half-life is represented as T1/2, it means how much time it takes for blood level of drug to decrease to half of what it was at equilibrium. This is due to drug being metabolized and eliminated. Clearance, denoted by CLR, is defined as theoretical volume of body fluids containing drug from which the drug is completely removed in given time. KE, known as first-order elimination rate. Ka, defined as first-order absorption rate. Volume of distribution, the theoretical volume that would be necessary to contain the total amount of an administered drug at the same concentration that it is observed in the blood plasma. CLT, is known as total clearance of drugs from body or total systemic clearance. Now let's talk about compartment models in a bit detail. Compartment model is group of tissue with similar blood flow and drug affinity. Compartment is physiologic or anatomic region. Compartment model simply interpolate the experimental data and allow on empirical formula to estimate drug concentration. It's of two types: 1 compartment open model, and 2 compartment open model. Classification of 1 compartment open model. It's of 4 types. OCOM for IV bolus administration. OCOM for IV infusion administration. OCOM for extravascular administration 0 order. OCOM for extravascular administration 1st order. In image we see when drug is administered in body, it has some administration rate, denoted by Ka, then it diffuses in blood and other body tissues, after that it gets metabolized and eliminated, where it follows elimination rate denoted by Ke. Classification of 2 compartment open model. It's also of 4 types. TCOM for IV bolus administration. TCOM for IV infusion administration. TCOM for extravascular administration 0 order. TCOM for extravascular administration 1st order. Here in this picture, drug is administered following first order kinetics Ka and perfused into Cc known as central compartment, and from Cc it goes to Pc known as peripheral compartment denoted by 1, 2, and from here it again goes to Cc and denoted by 2, 1 for elimination following Ke, rate of elimination. Applications of compartment models. Useful in plasma drug level and therapeutic and toxic effects in body. Characterizing behavior of drug. Calculating optimum dosage regimens. Evaluation of bioequivalence. Useful in drug concentration time profile in both normal and therapeutic conditions. Now let's talk about methods of elimination. Criteria. Approximately 10% drug should be excreted in urine unchanged. Metabolites should not interfere in analytical method. Water loading dose is given to promote diuresis and collect blank volume of urine sample. Bladder should be emptied completely. Volume and time of urine sample must be noted. It should be collect for 7 biological half-life of drugs. Now it's of 2 types is being discussed. 1. Rate of excretion method. Rate of urinary drug excretion dxu dt is directly proportional to amount of drug in body, x. dxu dt equals kex. As per first order disposition kinetics, x equals xoe ket. dxu dt equals kexoe ket, log dxu dt equals log kexo ket, 2.303. It can be used for drugs with long half-life. Now here graph is shown for this elimination rate. 2. Sigma minus method. In estimating K, fluctuations in rate of drug elimination are not observed. dxu dt equals k, ex, oe minus ket. xu equals kexo, ke, 1 minus e minus ket. xu equals cumulative amount of drug excreted in urine unchanged. At any time t, time approaches infinity. xu infinity equals kexo, ke. xu infinity minus xu equals xu infinity e minus ket. Log, xu infinity minus xu, equals log xu infinity minus ket, 2.303. xu infinity minus xu, equals amount remaining to be excreted at any given time. Here the graph is shown between time and xu for this model. Now in next video we will discuss in detail about first compartment open model and second compartment open model with equation and easy to remember note. Thank you for now. Please like and subscribe the channel. You can also share it. Thank you. Bye bye. Stay in home. Stay healthy.